think so. Can you hear me?
Okay, so for our second talk of the morning, we're happy to have Thomas Sotiriou, who was a postdoc here, right? Yeah. And he's at University of Nottingham now, and will be telling us about black holes and Lorentz violations.
Okay, thanks. It's a great pleasure to be here. So yeah, I was that postdoc back in 2007, 2009, which, you know, I regrettably realized it's almost 20 years ago now. It really, I think, changed my perspective of physics. I'm going to save this type of comment for tomorrow at dinner time. I decided to talk about black holes and Lorentz violations, even though I haven't really worked in this field for the last decade, because I think that has been quite influential in that. So I wanted to, someone needed to talk about this. So back in 2001, Dave and Ted introduced Einstein-ether theory. And I believe the logic behind it was that we're testing Lorentz symmetry with very high precision in the standard model, but it could be broken in gravity, and there should be some effective theory that describes this and allows you to quantify Lorentz violations in gravity and obtain bounds and so on and so forth. And the logic here was that you can introduce a covariant theory that has a unit time-like vector field. It's the most general action. You can write up to second derivatives of that vector field. And by doing that, you can introduce in your space-time a preferred threading by time-like curves. So that's the closest thing you can get to the kind of the idea of an ether in the proper context of a field theory, and the idea of having a preferred observer. So I think this theory has served very well in terms of quantifying the constraints of Lorentz symmetry breaking in gravity by bounding these various coefficients, C1 to C4. Then in 2009, Petr Vozava introduced a different Lorentz breaking theory that was interesting. The motivation and the logic here is different, so that it's breaking space-time back into space and time, introducing a foliation, and using the residual symmetry foliation preserving diffeomorphisms as the defining symmetry of your theory. And the benefit of that is that now you can introduce, in a well-defined way, additional spatial derivatives of your field, and hence modify the propagators so that Lorentz symmetry breaking acts as a field theory regulator, and you get a renormalizable theory of gravity. So T now is kind of the preferred time in this foliation, and you can go and write down all of the terms. L2 has all of the terms that are second order in derivatives in this preferred foliation. So you get to, so that would be one in general relativity. That's a three curvature. So now it's generalized to a general coupling, and we say, it's just the derivative of the logarithm of the Laplace function. So that's the whole set of operators. But then you have four spatial derivatives and six spatial derivatives, and dozens of terms with this in L4 and L6, which are, as I said, there to change the propagator at high energy. So I'm not going to spend any time talking about the UV properties of these theories. I'm going to be more interested in kind of the low energy limit of it, which is with the action L2. And kind of a year after Vozava introduced it, Ted showed that you can write this in a covariant way, and that it bears relation with Einstein-ether theory. So the logic here is that if you start with the action that I had in the previous slide, and then you force the ether to be hypersurface orthogonal, and the normalization is set by the unit constraint that I had in the previous slide, then that part, the L2 part of the action, really becomes the same as Einstein-ether theory, except you're imposing this before the variation. So it's not the same theory, that you can put it in the same form. The hypersurface orthogonal solutions Einstein-Ether theory, then will be solutions of Kosawa gravity in the low energy limit. The converse is not necessarily true. So these, and in contrast to Einstein-Ether theory that introduces a preferred threading, here I have a preferred slice, I have a preferred foliation. So these are both interesting ways to break Lorentz symmetry, and you can create well-defined theories out. Now, I want to talk about black holes, so that what is interesting is the causality in these theories. And there are two scenarios that can happen here. So when I break Lorentz symmetry, I stick to a theory that has linear dispersion relations. What I can actually have is different speeds for different fields. And if I restrict myself to a theory that's second order in field equations, like Einstein-Ether theory is, this is where I'm going to end up being, right? So I can, my excitations still have speeds that are bound from below, they're just different. And in fact, they propagate, massless excitations propagate along the null bones of effective metrics, right? And this is how it works for Einstein-Ether theory. Basically, different excitations have propagated in effective metrics, which are composite coming from the actual metric that you wrote the theory with, and pieces of the ether, and SI is the corresponding speed of propagation. And the way, now, it then becomes kind of intuitive that what happens to black hole, the notion of black holes in this theory. So what you have is, instead of having a single horizon, which is horizon of G mu nu, you actually have a succession of nested horizons of the different metrics, G twiddle, or the different fields, and have different propagations. And that was discussed by Chris Healing and Ted back in 2006. So the notion, interestingly, the notion of a black hole survives in this type of theories by having this succession nested horizons. Now, things are a bit, more confusing when you think of modified dispersion relations, right? So if you have a higher order dispersion relation of this type, then if I go to high enough K, high enough momenta, then I can propagate arbitrarily fast, right? So the picture that I just described should not make any sense anymore. In fact, I should have kind of a pre-relativistic picture where I have that a leaf of the preferred foliation, which I need in order to have a well-defined dispersion relation, and then everything that's north of the leaf is really in the future. Everything that is south of the leaf is in the past, right? And that leaf of the foliation acts as a surface of simultaneity. Now, there are two puzzling kind of thoughts you could have here. The one is that that the limit from a causality perspective, that the limit where this coefficient here alpha goes to 0 seems kind of discontinuous, right? Because if I set alpha exactly 0, then I cannot recover this relativistic type causality. I might have this multiple metrics, but at the end of the day, everything has finite propagation. Locally, there are propagation cones for all my excitations. Whereas if I have an arbitrarily small but non-zero alpha, I will always be in that picture, and that's kind of disturbing, right? The other thing is that, of course, the notion of a black hole or a horizon doesn't seem to fit in that second picture, right? With this type of relation. So the solution to this first puzzle is really hidden in the fact that when you write the low energy limit of if I think of L2, I'm basically killing the modified dispersion relations. I'm going back to linear dispersion relations in this theory with the preferred foliation, right? And I should encounter that puzzle that I just said, but the fact that I don't is really hidden in the fact that when written in a covariant way, I pick up an extra derivative here. So this is not a purely second order theory anymore when seen in a covariant formulation. And indeed, if I see, for simplicity, if I just go to a spherical symmetric setup, so now we do 1 + 1, and I try to set up an initial value problem in that setup, what I end up having is usual kind of second order propagation equations, constraint equations, but I also have an additional equation, which is elliptic, and it's not a constraint. And I've written it here, so I mean, I've basically gone to the preferred foliation. I've written the metric in this notation, N, S, N, R, and the radius R are now functions of T and capital R, right? And there's way too much notation that I haven't explained in this slide, so always about that. So forget about the shorthand notation here, but the idea is that the kind of what would be the T equation now becomes a purely radial derivative of something that is equal to 0, which is not a constraint. So as I try to use my initial, my evolution equations, suppose I try to prescribe a free evolution scheme, suppose I solve my constraint equations in the initial surface, I now have evolution equations, but in addition, I have this equation which I need to solve on every slice to go through. So you can think of it, say, as an equation that prescribes the lapse, which is because I have reduced symmetry, right? So this is like an instantaneous mode, and you can find it in the perturbative treatment as well. It kind of propagates data along that slice, and it tells you that your low energy theory, even though you have killed the higher order dispersion relation, remembers that there is infinite propagation because it has this instantaneous mode.
Is this system of equations in some sense well posed?
Hopefully, I mean, in the sense that there is no proof that the hyperbolic part is well posed.
Right. But worry about the elliptic.
Yeah, but I mean, the elliptic part, if you prescribe initial conditions, boundary conditions as you'd expect, then that's not a problem. I mean, this is just a linear equation now.
There's 1 + 1, so you impose a spatial boundary condition on one spatial.
No, on every slide.
On every
slide.
Oh, of course.
Yeah. Okay. Yeah, of course. Yeah. That's what you have to do here to kind of close the problem. Now, so that kind of takes care of the first problem, and it tells you that even in the low energy limit of the theory, you still have this notion of infinite propagation. It lingers on. Now, what happens to black holes then? The black holes don't exist in this theory. And that kind of brings down the second interesting notion with this, which is that black holes do exist, and that there is a different type of horizon in this theory. It's called the universal horizon. So, the first time my knowledge that this term universal horizon came about was in a meeting in Paris, one of Ted's favorite places, and I managed to fish out some pixels from that meeting. So this is with the people involved. So this is Ted, myself, and Sergei Sibiriakov, and we're in the village church in some play. I have no clue, no recollection what this play was about or why we dressed funny. I don't know, Ted, if you remember. But I do know that Diego Blas was supposed to be my wife in this play. And somehow we're in a wedding bed here. So that's all I remember from that play. Anyway, so in that meeting, Sergei presented was doing a calculation without back reaction in this setting in the low energy limit of Osama gravity, and he was trying to basically solve the equation for this T, right? The scalar field that defines the foliation on a Schwarzschild background. See how T behaves without taking into account the back reaction of the field. And he presented some preliminary results and showed that one of the constant T slices appears to become a constant R slice as well, which is kind of puzzling, right? Because then you kind of think that if I move to the next one, I can go further up. And at the time, Enrico Barausi, Ted, and I were actually revisiting kind of the full problem with back reaction numerically. And we went and looked at that, and this is what I'm showing you here. So this is an RT diagram. So these are static spherically symmetric solutions, which, because they're spherical, they have a surface orthogonal, and hence they're solutions of both Einstein ether theory and that low energy limit of Osama gravity. Because the ether is always have a surface orthogonal. And so this is a TR diagram. This would be kind of the killing horizon of the metric. the dust line. And now the colored surfaces are constant preferred time surfaces or surfaces normal to the ether. And I've colored them in such a way that they get darker as I go forward in time. And what you notice now is that if I look in this region, the surfaces all go to spatial infinity, right? But on the other end, they kind of asymptote to a constant R surface, which is actually a constant preferred time surface as well, right? They don't go further in, and then all of the next surfaces, of course, asymptote to that same red line on the other side. Which means if I start moving, so if I think of being somewhere in space time here, and I try to emit any information, I try to propagate something, then of course I should find myself somewhere in the darker green surface if I'm going somewhere in the future. And if I'm sitting out here, it's nice because there are darker green surfaces that span the whole exterior, so I can send information to the whole exterior, right? But if I were to try to emit something here, say, I need to move the darker green surface, I need to move further in. So that red surface basically acts as a horizon, as a boundary for me to be able to send information, even if I'm doing it with infinite speed, because time needs to run forward in the preferred foliation, and all of the time forward is inside the boundary.
By killing horizon, you mean with respect to one of the metrics?
Yeah, that's the killing horizon with respect to G mu, so that would be for ordinary matter.
There's a lot of metrics.
Yeah.
You could move that around. Right?
Yeah, great question. Yeah, I mean, there are other killing horizons. They all are outside the red. Okay.
Is the red one the spin zero horizon?
No. That's the universal horizon. So the spin zero horizon, depending on whether the spin zero mode is faster or slower than light, could be right or left of what I can call here the killing horizon. Okay.
So that's different.
Yeah. Okay.
If the metric is no degenerate, it's always outside, strictly outside.
All of the killing horizons of the effective metrics lie outside the red. That's basically the same thing plotted. So that's from Diego's and Sergei's kind of decoupling calculation that they eventually published, which is basically the same slides as now, from the Schwarzschild diagram. And now, after that, people have looked into kind of rotating black holes, and the rotating black holes so for rotating black holes, solutions to Horava gravity and Einstein ether theory do not coincide, because the ether doesn't want to be hypersurface orthogonal in Einstein ether theory when there is rotation. Whereas slowly rotating black holes in the Horava gravity have been actually shown to have these universal horizons, and these universal horizons have been shown to exist in three-dimensional black holes in Horava gravity with arbitrary rotation, and have been shown to also exist outside the Sitter horizon and kind of play cosmological kind of role. So they do seem to be pretty generic in theories with the preferred foliation, whereas they cannot really be defined in theories with the preferred threading. Because I said, the moment you go away from rotation, there is no preferred foliation associated with that threading. And again, fairly recently, Ted, together with Adam Figueras and Wiseman, they kind of were the first to find fully, rapidly rotating black holes in Einstein ether theory. Okay. Now, sticking now a little bit to theories with a preferred foliation, it's kind of interesting. It's kind of interesting that you can give a global definition of these universal horizons in exactly the same way that I would do in general relativity. If you generalize appropriately your notion of future and prime, right? So that's obviously the future, the causal future in a relativistic theory. right? And if I just now accept that here, anything that lies north of a leaf of the preferred foliation is the future, because I have infinite propagation. And if I, instead of considering scry as null infinity, think of scry as the unit of all of the points at infinity at every spatial slice. So I create a scry, which is just the union of all the points at infinity of every leaf in the preferred foliation, because this is where I can communicate with it with that infinity instantly. Then in fact the usual definitions apply, right? So I can define the universal horizon as an event horizon, future and past, right? I can define a black hole in exactly the same way, and in fact I can prove that this type of event horizons are actually leaves of the foliations. And in fact, they're leaves that do not reach that my notion of scry, that spatial infinity, which is kind of interesting. If I impose axisymmetry, I can find a local condition which reminds me of the fact that for stationary black holes in general relativity, the event horizon is a killing horizon. So it turns out that you can prove that the ether, the normal to the foliation, dotted with a killing vector chi, you associate with stationarity, vanishes on the universal horizon, provided that the acceleration of the ether dotted with chi is not zero. So that's a bit like the degeneracy condition, and A dot chi seems to act like the surface gravity, and people have thought about this in the context of thermodynamics. And if you impose axisymmetry and introduce a circularity assumption for your
This A dot chi non-zero, can you map that to one of the standard notions of surface gravity for ordinary killing horizon?
Well, yes, but there is a lot of discussion, I think, and Stefano is probably a lot of expert.
Kappa peeling of the universal horizon is exactly the peeling surface gravity of the constant.
So for an ordinary killing horizon,
constant T surface. Yes, it's exactly Kappa peeling, and
okay,
we can show that.
Yeah. So if I assume the usual circularity conditions on the killing vectors, then I can prove that if there is a universal horizon, there will be this accession of killing horizons in the exterior. Right, so it will be covered by a killing horizon as well. Now, the next question you can ask is, okay, but does this really form from collapse, and is it really stable, right? So David Garfinkel, Chris Illing, and Ted did the first collapse, and the only, I think, proper collapse simulation in this context. Back in 2007, so before Hosoba gravity was introduced. So that was a spherical collapse simulation in Einstein ether theory. And did it find that you can form these spherically symmetric black holes in Einstein ether theory, which we later know that they're black hole solutions in Hosoba gravity as well. You can form them from collapse. That was collapse of a scalar field into the black hole. Back then, obviously, they didn't know about the universal horizon. They didn't know about Hosoba gravity. This simulation is done in the foliation, that is normal to the ether. So in the native foliation of Hosoba gravity, accidentally. And so collapse is not generally the same in the two theories. And that's the equation I wrote before for that instantaneous mode, right? And now I can explain that, but this short-term notation is this AE is really AE equals 0 is the ether equation in Einstein ether theory, right? Whereas this is the equation of Hosoba gravity. So I kind of written one in terms of the other, right? So this is the equation in Hosoba gravity of the instantaneous mode, and since it's a linear equation in the radius, I can integrate it on all slices, and what I get is an integration constant per slice. And this S is just the projector in the direction normal to the ether, right? So long story short, if this f of t were 0, then I would be effectively imposing Einstein, this condition would effectively be telling me that the Einstein-Ether equations are that the ether equations in Einstein-Ether theory are satisfied, and the two theories would collapse in the two theories would be the same. Dynamical evolution, spherical evolution of the two theories would be exactly the same, right? So they only differ in the fact that Einstein-Ether theory, for Avogadro, has this extra instantaneous mode, and basically I need to solve this additional elliptic equation in every leaf. The trivial solution, one with the trivial boundary conditions, basically. With the trivial f, just makes the two theories the same. And if I were to impose regularity at the center of the configuration everywhere as my boundary condition, then I could send this f to 0. I would have to send this f to 0, and hence collapse in the two theories with a regular center is the same, right? But of course, so what Ted, Garvin, and Neeling have done is basically done collapse in Einstein-Ether theory, which also covers the Fosava case if you impose the depth of T is 0. So this particular subset of collapse simulation. It is hard to, in these simulations, they actually seem to be finding that the lapse goes to 0 somewhere inside the universal, or approaches 0 somewhere inside the universal horizon, which would be the condition for the formation of this universal horizon. But of course, they can't really see that because they're in this formulation where the universal in this foliation where the universal horizon is infinitely into the future, right? So an interesting thing to do would be to redo that simulation in Einstein-Ether theory in a different foliation that actually penetrates the universal horizon, and then you could actually see if it forms in a finite time. So that's something that seems mathematically doable. Now, there is the question of whether this universal horizon is stable, and this question comes about kind of intuitively by the fact that it looks more like a Cauchy horizon in the corresponding initial value problem, right? And we expect Cauchy horizons to be unstable in GR. And what I mean by that is that, as I said, that you need to solve that equation for any given slice, which means you need boundary conditions, and I can prescribe boundary conditions for the exterior. I can prescribe boundary conditions asymptotically, right? For the exterior region, but actually the universal horizon, as I've told you before, is a leaf of the foliation that doesn't reach spatial infinity, and hence, how do I prescribe boundary conditions from that point onwards? You know, and so in a sense, it kind of makes sense that something has to go wrong there. Otherwise, I need to prescribe what is happening in a different asymptotic region, basically, to be able to continue evolution inside. And Blas and Sibiriakov have found some sort of tentative evidence there might be an instability on the universal horizon, but there is no conclusive proof. Now, one interesting kind of direction in this is whether you can use these black holes to build perpetual motion machines, right? And whether that's kind of an internal inconsistency of Lorentz breaking in gravity. So if you think of let's forget about the universal horizon for a moment. Think of these multiple kind of nested horizons that we talked about, and you now have two fields which propagate at different speeds. They see different horizons, right? Call A field the slower field, B field the faster field, right? And they propagate along null cones of an A metric and a B metric, right? And so that then would be kind of the causal diagram of the B metric, where the blue line is the horizon for the B field, and the horizon of the A field would then be lying out here, and the region between them, even in spherical symmetry, would look like an ergo region. And you could so this discussion started in 2006, where Dubovsky and Sibiriakov kind of came up with this Gedanken kind of experiment in the context of, back then they were not thinking of Einstein-Ether theory of Avogadro, they were thinking of false compensates, but the setup was basically the same, and the logic was that if I can go and assign kind of a Hawking radiation temperature with the two horizons, then the temperature actually depends on the speed of the field. That's what they saw. The temperature depends on the speed of the field, and I could actually use the two kind of different types of Hawking radiation of different temperatures to communicate with reservoirs outside and transfer heat from the colder reservoir to the hotter reservoir by using the black hole as a conduit, and hence violate the second law of thermodynamics. Ealing, Foster, Jacobson, and Hall then kind of demonstrated that there is a classical kind of analog with this where you can run a Penrose-like process. So I take a particle, I send it in this ergo region, and it splits in A and B particles, and then the B particle can still escape the A horizon. So the B particle comes out, carries away some energy. The A particle carries negative energy in, and hence I can actually mine energy in a Penrose-like process using the fact that I have two horizons for the two different species. And this doesn't sound as disturbing initially, because if you could actually, we do that in the Penrose process, right? And the idea is that kind of in every step, I reduce the size of the ergo region until it actually disappears. And hence you could think that the same thing could happen here. I basically change the configuration of the ether till the ether goes to kind of a zero configuration, and there are no multiple horizons and everything is fine. The problem is that you can't really do that because the ether satisfies the unit constraint, and it doesn't have any free parameters, any conserved charges for you to mine in this setup, right? Unlike, say, the angular momentum of a black hole in the Penrose process. And indeed, both of these assumptions, both of these processes make some assumptions about the state of the black hole and the entropy and so forth, and what it depends on. Now, in 2016, we saw together with Dave and other people that kind of classical Penrose-like process, cannot really happen generically. So there's an obstruction to it, which is the following. You need to make sure that as you do in the standard Penrose process, that the B particle can escape to infinity, and the A particle can actually fall in, right? For it to happen. And so what we did is we actually went and checked that and looked, and for this to happen, there is a condition that needs to be satisfied for the killing vector, between the killing vector and the B metric. In fact, which you can really kind of interpret physically as that in the ergo region, gravity should continue to be attractive in terms of the bit metric. So the norm of the killing vector could not be less than -1, basically. And it turns out that all known kind of configurations that we had in Einstein-Ether theory or for Avogadro don't actually satisfy this condition. So you can't really run that process in these spacetimes, right? So there is a sort of obstruction that and hence maybe the field equations know about this, right? And you can run that in physical configurations. It doesn't say anything about the Hawking radiation argument, right? And it's about a single part. I don't know if you could do that with more than one particles or whatever, more than one splits or whatever else, right? So obviously it's not a conclusive argument, but I think this is still something interesting to explore. You could also ask yourself, I don't necessarily need to have a preferred foliation or a preferred frame to end up in a situation where I have multiple horizons. All I need is derivative interactions between my fields. Because in a black hole spacetime, I'm in a non-trivial configuration, so I can have different speeds from different modes because they just have derivative interactions with each other. And that can happen very easily in an EFT, basically, with derivative interactions. It turns out that you can prove that even though you can have different metrics with different propagation speeds, in the context at least for a scalar field with derivative interactions, killing horizons will always coincide, and you cannot create this perpetual motion from the issues there. In the sense that the killing horizons of the metrics, even though they're different metrics, will be in the same location.
Are you talking about Lorentz invariant derivative interactions now, or
Yeah, I mean,
like higher curvature?
covariant derivative interactions in theory is that make Minkowski vacuum with zero fields. Yeah.
But like you're not trying to explicitly violate Lorentz symmetry.
No, exactly. That's what I'm saying. That I don't need to do that. I could have these nested horizons without really violating Lorentz symmetry in the sense of locally.
But would that just happen in a generic higher curvature gravity theory?
It does. Yeah, it does happen. Yeah. So I mean, the proof it doesn't happen here. That the killing horizon that I'm talking about here is not for a higher curvature gravity theory. It's for non-minimally coupled scalars with derivative interactions, right?
Thomas, but for example, in Nordesky, gravity and matter, I mean, it's the way to put constraint on Nordesky. Gravity and matter have different.
Yeah, exactly.
So you're saying that still the killing horizon coincide.
Right. Yeah. Yeah. So I mean, we saw that back in 2018 for spherically symmetric spacetimes, and it was very recently generalized in rotation by Follett and Ulrich in a very nice paper. Okay. Now, an interesting kind of problem arose when people started looking at slowly translating black holes theories. And the reason they looked at slowly translating black holes is because they were actually trying to build up a framework to constrain Lorentz symmetry with gravitational wave observations and gravitational waves in spirals. And you need to calculate now some parameters called sensitivities which control gravitational wave emission in additional polarizations in the spiral of the gravitational waves, and they relate to the charges, the additional charges you have. And to calculate them, you really need locally to understand how to get the solution for a translating black hole. And so Ramos and Barause studied this problem kind of numerically in its full glory, numerically with back reaction, try to basically found slowly translating analogs to the spherical symmetric and static black holes, and found that so this is just a linear approximation basically in the velocity, and found that there were curvature singularities on the spin zero horizon. That's the horizon for the scalar modes that we already have. Right, for solutions with flat asymptotics, and they also found a curvature singularity at the universal horizon, which persisted even when they relaxed the flat asymptotics. So they kind of concluded that for generic parameters of these theories, there seem to be no slowly translating solutions, which kind of seems to be a fundamental problem. However, far more recently, just last year, Kovacs and Sibiriakov looked at the same problem in a kind of a simpler setting, with no back reaction. So you take the Schwarzschild black hole, you translate it, and then you try to solve the ether or the foliation equation on that background, and did not find any singularity in the spin zero horizon, and at the same time, also the ether, the hypersurface orthogonal ether is regular also on the universal horizon, except there is some sort of weak branch point singularity, which means you can't really extend. So it scales like a power, basically, of the coordinate there. And hence, even though it's singular, it's regular, its derivative is regular, higher derivatives are singular, and then you cannot continue the solution past the universal horizon. But it's regular on the universal horizon. which kind of seems to be in disagreement with the previous result. So and it's not clear if it's a kind of a numerical issue or an issue with approximation when you have back reaction, or something like that. So this is still kind of an open problem. Now, I'm gonna close here with some remarks and explain why I mentioned this thing with the translating solutions at the end. So I think it's kind of a pretty remarkable thing that the notion of a black hole, as we understand it, survives when we have Lorentz symmetry breaking, even when we have very violent Lorentz symmetry breaking, some kind of an infinite propagation, instantaneous transmission of information, and so on and so forth. There is, of course, plenty of things that we don't understand, especially about universal horizons. There are first constraints in Lorentz symmetry breaking in the standard model, which are very, very stringent. The logic here is very much that there is some sort of mechanism that suppresses, the percolation of Lorentz violations from gravity to the standard model in this context. On the gravity side, there's a very tight constraint from the propagation of gravitational waves, but that kind of restricts one direction in a multidimensional parameter space. So interestingly, there's still models, there's still kind of choices of couplings within these theories that are viable and allow for large Lorentz violations. If by large, I mean that the additional degrees of freedom can propagate at 1,000 times the speed of light. So in this sense, they're not close to general relativity in any way. And there's a lot more work in this area, in part because this constraint from kind of gravitational waves has been seen as kind of killing Lorentz symmetry breaking, but that's, as I just said, not entirely true. And in part because that discussion about translating black holes, at least in the people who work in this topic, was kind of very puzzling. It's like, is the theory, does the theory make sense or not, right? And I'll close by saying that there's also plenty of exciting work that I didn't talk about here. So there's a lot of work by many people in the room on black hole thermodynamics in the context of Lorentz symmetry breaking. And there's also a lot of work about UV completion and whether, especially in the context of Kosawa gravity, and there has been papers showing that this is actually a renormalizable theory beyond power coupling, and so on and so forth. So it is, one has to say that it is a kind of quantum gravity theory, a renormalizable quantum gravity theory that you can write the action for in one line, or maybe 3 lines. So it's kind of an interesting model. So I'll stop here.
Okay, questions? We'll start with Ted.
I have a question and a comment. The question is about the Penrose process. If I remember right, Aaron and I wrote another paper after that one, where we considered the original Penrose process idea, which he wrote about, and before he talked about this splitting particles, was lowering particles on a rope into the ergo region.
Yeah.
And I just wondered, you have to imagine an idealized rope that can do the job and hold the particle. Yeah. But putting that question aside, does the issue that you described that invalidated the Penrose process in this particle trajectory version, does that somehow also apply to the rope lowering version?
I think it could, in a sense that the rope or how the particle comes in doesn't. It's not the question. The question is, in the rope you were releasing.
You lower it and then you drop.
Yeah, but basically there was a split even afterwards, right?
No, I think you just lower something into the ergo region, extracting energy, and then you drop the thing from the end of the rope and pull the rope back out.
I don't know. I need to think about it because the condition of whether. So I think you were releasing the rope was made from B matter basically, and you had it in the box A matter.
Yeah. Yes.
Yeah. I think the condition for the A matter crossing the horizon might still be a problem, because I think the obstruction was whether the B matter actually crosses the universal horizon, and the B matter, you can pull out basically the B matter, right? So I mean, I don't think we consider it explicitly. We're focused on the other thing. But Dave, do you remember?
I'm in the same boat as you. I'd have to think about it. I don't know whether the instruction would hold with different, because we had a sort of a free fall kind of like trajectory of just throwing in. Yeah, I'll think about it.
Okay. And the comment I just can't resist making. So I think it might have been just a few days after Aaron got to Maryland as a graduate student. And I might have given a talk on unseen ether theory, I think, and he asked a question about a translating black hole, or just uniformly translating particle through the ether, and whether it experiences like friction, or whether the law of inertia applies in Einstein ether theory. And I was embarrassed then not to know the answer. And 20 years later, I am even more embarrassed to not know the answer. And I just have to comment that you would think, so the work that was done with Pau Figueres and Toby Wiseman, they did this incredible numerical methodology to find the rotating black hole solution. It's got very peculiar properties. It's not a killing horizon that it has, but it's definitely a solution. So then they thought, well, now let's do the translating black hole, not small velocity, but arbitrary velocity. And they couldn't succeed so far in adapting their numerical method to the translating case, because lacking the reflection symmetry about the equatorial plane of the rotating case introduced a problem in setting up the numerical method the way they were doing it. And they literally just sort of got stuck, as far as I know, so far. So we also don't even know from that numerical methodology the answer. And I have a deep fear that like there just isn't, that Aaron's original question actually was very perceptive, and that there is something pathological even in that simple setting.
I'm not entirely convinced that there is something pathological in the setting. I mean, it's definitely harder to do it, to do the kind of numerical computation. And part of, I think, the problem, at least the way I understand it intuitively, is that, of course, when you have when you take slow rotation, the rotation falls off asymptotically. So there's, that you can still deal with asymptotics and all this kind of stuff. When you take a slow translating case, there's kind of an ambient heat. And it becomes a lot more hairy what happens in asymptotics, right? So I mean, I think this could be part of the confusion of what is happening, contributing to both the numerical difficulties and also the conceptual confusion of how to deal with this problem. It's not even clear to me if in the context of having translating ether, in the context of the black holes, in an ether environment, whether you need to be imposing flat asymptotics and so ether alignment asymptotically, because if I have the other black hole, whenever I'm going to do the near region matching of this, there's not going to be an aligned ether anywhere. So I mean, so I don't know. I think it's a hard problem, but I'm not yet convinced that there is some sort of fundamental issue with slow translating ether. I think it is a real problem. I think there might be a fundamental or a very deep problem, in the sense of, if I have a preferred foliation and I have multiple black holes, right? How does it configure itself so that the universal horizon behaves in the way I said, and it's kind of the last leaf that makes sense? How does it happen to be for different black holes that form at different times, and so forth? I mean, there is a bit of mind-boggling thing there, and how do I get a global foliation with all of these different problems, right? I mean, that's really hard. Okay, one more question.
Yeah, comment on a question. The comment is concerning the fact that you can go beyond the eternal black hole, and you can define the dynamical universal horizon. So basically, you decompose in U, you have the orthogonal vector S, and you have basically a surface. And you can prove that what is the expansion that is zero on the dynamical horizon is theta S. And basically, you can have a future and past, outer and inner trapping universal horizons. In that case, you have basically that your black hole, your trapped region, can be a kind of cyst inside the Minkowski spacetime, right? And you have all these leaves that get around this blob. So this is, I think, is relevant for the problem of the boundary condition at infinity, because there the horizon, normally the universal horizon in the eternal situation basically links to I plus on both sides. And here instead, there would be really at a finite distance sandwich always between killing horizon. And if it evaporates, there cannot be an extremal universal horizon. You implicitly say that because I dot chi cannot be zero for any universal horizon to exist. So, and it's very interesting this. So I wanted to ask you if you have any thoughts about how you would treat the boundary condition in such a dynamical problem, because it looks to me that in that case, you have all the leaves that reach I naught, except basically these concentric leaves, which are the boundary of the dynamical trapping horizon, universal horizon, and the interior.
Yeah, no, I mean, I don't really have any more thoughts than what I said before. That it seems strange what be prescribing boundary conditions,
But you can flip the boundary, right? So we're talking about the elliptic mode boundary data are going across. So the point is we're so used to prescribing boundary conditions at asymptotic infinity, right? But in this case, since it's a leaf, in your original diagrams, the interior and exterior leaves of the foliation, they both asymptote to the universal horizon, right? So what you can do actually is you can prescribe boundary conditions at infinity for the exterior, and then you can prescribe regularity right around the universal horizon on the other side of the boundary, okay, as you go from outside to inside leaf, and then use that to then get you to the inside leaves and then continue to evolve from there for where the inside leaves asymptote on the other side. So in other words, regularity of the universal horizon allows you to bridge that gap in terms of how you're prescribing the elliptic data, because the elliptic data can be prescribed at either boundary. Yeah. There's no bulk here. There's nothing you have to worry about. It's direct boundary to boundary data.
Yeah.
So that's how it's answered.
This kind of reflects the fact that the universal horizon is at n equals 0.
Yeah, right. Exactly. Yeah.
So if you impose regularity basically there as well, I mean, at least the stationary problem.
Yeah, right.
But I mean, whether all of this translates, I mean, I really agree with that, but whether it translates to the full initial value problem and all this kind of stuff, I don't really know.
Okay, so let's thank Thomas again for the talk.